Welcome to our next lesson on machine learning, where we will delve into the fascinating world of unsupervised learning, specifically focusing on clustering techniques. I can't wait to begin our lesson, so let's start on the next slide. Throughout this lesson, we will explore the following key topics to enhance your understanding of this essential aspect of machine learning. Clustering basics. We will begin by establishing a solid foundation in the fundamentals of clustering, discussing its purpose, applications, and the various types of clustering algorithms available. K-means clustering. One of the most widely used clustering algorithms, K-means, will be thoroughly examined. We will learn how this algorithm partitions data into K clusters based on similarity and discuss its strengths and limitations. Hierarchical clustering. Next, we will explore hierarchical clustering, a technique that builds a hierarchy of clusters based on the similarity between data points. We will cover two main approaches within hierarchical clustering. A. Agglomerative clustering, starting with individual data points as separate clusters. Agglomerative clustering progressively merges the most similar clusters until a desired structure is achieved. B. Divisive clustering. In contrast to agglomerative clustering, divisive clustering begins with all data points in a single cluster and iteratively divides them into smaller clusters based on dissimilarity. Cluster validation. Finally, we will discuss the importance of evaluating the quality and validity of the clusters obtained through various clustering algorithms. We will introduce techniques and metrics used to assess the goodness of clustering results. By the end of this lesson, you will have gained a comprehensive understanding of clustering in unsupervised learning, empowering you to apply these techniques to real-world problems and unlock valuable insights from your data. Clustering is a method that allows us to group similar data points together based on their inherent characteristics, without the need for predefined labels or categories. It's like letting the data speak for itself and reveal its natural structure. One of the key aspects of clustering is its exploratory nature. It falls under the umbrella of unsupervised learning, which means we don't have a specific target variable to predict. Instead, we let the algorithm discover patterns and relationships within the data on its own. It's like embarking on a journey of discovery, where we let the data guide us to uncover hidden insights. Clustering can also serve as a valuable precursor to supervised learning methods. By identifying distinct groups within the data, we can gain a better understanding of the underlying structure and potentially use that information to enhance the performance of supervised models down the line. Now, let's talk about the concept of similarity or closeness in clustering. To group data points together, we need a way to measure how similar or close they are to each other. This is where distance metrics come into play. We can define similarity based on various factors, such as Euclidean distance, Manhattan distance, or even more complex measures like cosine similarity. The choice of distance metric depends on the nature of the data and the problem at hand. It's important to note that clustering follows an iterative approach. Different clustering algorithms may yield different results, as they have their own way of optimizing the grouping of data points. It's not a one-size-fits-all solution, and it often requires experimentation and fine-tuning to achieve the desired outcome. When it comes to the types of clustering, there are primarily two categories: partitional and hierarchical clustering. Partitional clustering aims to divide the data into mutually exclusive sets, where each data point belongs to exactly one cluster. It's like partitioning a cake into distinct slices, where each slice represents a cluster. On the other hand, hierarchical clustering creates a nested structure of clusters, often represented as a dendrogram. It's like building a family tree, where each branch represents a cluster, and the leaves represent individual data points. Hierarchical clustering allows us to explore the data at different levels of granularity and understand the relationship between clusters. In summary, Clustering is a powerful tool for exploring and understanding the inherent structure of data. It enables us to group similar data points together, even without predefined labels. By defining similarity measures and employing iterative approaches, clustering algorithms can uncover valuable insights and serve as a foundation for further analysis and modeling. As we continue our journey into the world of data science and machine learning, clustering will undoubtedly play a crucial role in helping us make sense of complex data sets and drive meaningful decisions. So, let's embrace the power of clustering and unlock the hidden patterns within our data. K-means clustering aims to partition a given set of observations into a predetermined number of groups, denoted as K, in a way that minimizes the variation within each group. This approach allows us to uncover hidden patterns and structure within our data, enabling us to make informed decisions and gain valuable insights. At the heart of K-means clustering lies the objective function, which seeks to minimize the sum of squared distances between each data point and its assigned cluster center. By iteratively refining the cluster assignments and updating the cluster centers, the algorithm converges towards a solution that minimizes the overall within-cluster variation. To measure the variation within each group, we employ the concept of within sum of squares. This metric quantifies the dispersion of data points around their respective cluster centers for each variable. By combining the individual group variations, we obtain an overall measure of the compactness and cohesion of the clusters. It's crucial to note that the clustering results are heavily influenced by the variability of the input variables. Variables with larger variances tend to have a more significant impact on the clustering process. To mitigate this effect and ensure fair representation of all variables, it is often recommended to scale or normalize the data prior to applying K-means clustering. This standardization step equalizes the contribution of each variable to the overall variation measure. K-means clustering is particularly well suited for clustering numerical data, such as a set of measurements or features describing objects of interest. The input to the algorithm must be in numerical format, and a distance metric must be defined over the variable space. Commonly used distance metrics include Euclidean distance, which measures the straight line distance between data points, and cosine or correlation-based distances, which capture the similarity between data points based on their angle or correlation. The output of K-means clustering consists of two key components: the centers of each discovered cluster and the assignment of each input data point to its corresponding cluster. These cluster centers, also known as centroids, serve as representative points for each group and provide a concise summary of the data within each cluster. By examining the characteristic of the cluster centers and the distribution of data points among the clusters, we can gain insights into the underlying structure and patterns within our data. As we delve deeper into the realm of K-means clustering, it's important to keep in mind that the choice of the number of clusters, K, is a critical parameter that requires careful consideration. Various techniques, such as the elbow method or silhouette analysis, can assist in determining an appropriate value for K based on the intrinsic structure of the data. In conclusion, K-means clustering offers a powerful tool for unlocking the hidden patterns and structure within numerical data. By minimizing the within cluster variation and discovering meaningful groupings, K-means enables us to make data-driven decisions and extract valuable insights. As we continue to explore the vast landscape of unsupervised learning, K-means clustering will undoubtedly remain a fundamental technique in our arsenal, empowering us to unravel the mysteries hidden within our data. All right, let's dive into the nitty-gritty of the K-means clustering algorithm, a powerful technique that helps us uncover hidden patterns and structures within our data. Picture this. You have a vast collection of data points, and your goal is to group them into meaningful clusters based on their inherent similarities. That's where K-means comes into play. To kick things off, we need to choose the magic number K, which represents the number of clusters we want to discover. It's like deciding how many compartments you want in your toolbox to organize your tools effectively. Once we have our K, we randomly select K data points as our initial centroids. These centroids serve as the starting points for our clustering adventure. Now, here's where the fun begins. We assign each data point to the cluster whose centroid is closest to it. It's like playing a game of find your nearest neighbor, where each data point finds its best match among the centroids. This step is all about creating initial groupings based on proximity. But wait, there's more? After assigning the data points to their respective clusters, we need to recalculate the centroids. A centroid is essentially the mean value of all the data points within a cluster. It's like finding the center of gravity for each group. By updating the centroids, we ensure that they accurately represent the clusters they belong to. Here's the kicker. We don't just stop there. We repeat the process of assigning data points to clusters and recalculating centroids until we reach a state of equilibrium. It's like a dance between the data points and the centroids, where they keep adjusting their position until they find their perfect partners. We continue this iterative process until the assignments of data points to clusters no longer change, indicating that we've achieved a stable clustering solution. At the end of this journey, we are left with two valuable outputs, the final cluster centers and the final cluster assignments of our training data. The cluster centers give us a concise summary of each cluster, capturing the essence of the data points within them. They serve as representatives of their respective clusters, allowing us to understand the characteristics and patterns of each group. Moreover, the final cluster assignments provide us with a map of how our data points are distributed among the clusters. It's like having a labeled diagram that tells us which data point belongs to which cluster. This information is invaluable for further analysis, interpretation, and decision-making. In essence, the K-means algorithm is a powerful tool that helps us make sense of complex datasets by organizing them into meaningful clusters. It's like having a personal assistant that tirelessly works to find a hidden structure within our data, making it easier for us to extract insights and make informed decisions. As we continue to explore the fascinating world of clustering and unsupervised learning, the K-means algorithm will undoubtedly be a valuable companion on our journey. It's a testament to the power of machine learning and its ability to uncover patterns that might otherwise remain hidden in the vast expanse of data. So, let's embrace the power of K-means clustering and unlock the secrets that lie within our data. With this tool in our arsenal, we can navigate the complex landscape of data analysis with confidence and precision, paving the way for groundbreaking discoveries and innovative solutions. As we delve into the intricacies of K-means clustering, one critical question arises. How do we determine the optimal number of clusters? This is a fundamental challenge that often requires a combination of domain expertise and data-driven insights. Choosing the right value for K is crucial as it directly impacts the quality and interpretability of our clustering results. Increasing the number of clusters without proper justification can lead to a reduction in overall error, but it comes at a cost. If we keep increasing K to the point where each data point becomes its own cluster, we end up with zero error, but we lose the very essence of clustering, the ability to group similar data points together. To tackle this challenge, two primary approaches have emerged in the data science community. The first is the direct method, which involves optimizing a specific criterion, such as the within cluster sum of squares. This method seeks to find the value of K that strikes a balance between capturing the underlying structure of the data and avoiding overfitting. One popular technique within that direct method is the elbow method. Imagine plotting the within cluster sum of squares against different values of K. As we increase K, the sum of squares initially decreases rapidly, but at some point the rate of decrease slows down, forming an elbow-like shape on the plot. The elbow point often indicates a good choice for K, as it represents the point where adding more clusters provides diminishing returns in terms of reducing the sum of squares. The second approach is the testing method, which involves comparing evidence against a null hypothesis. This method treats the choice of K as a hypothesis testing problem, where we assess the statistical significance of the clustering results. By comparing the observed clustering to what we would expect under a null hypothesis of no clustering, we can determine whether the chosen value of K is supported by the data. Various statistical tests and techniques, such as the gap statistic or silhouette analysis, can be employed within the testing method framework. These tests provide objective measures of the quality and stability of the clustering results, helping us make informed decisions about the optimal number of clusters. It's important to note that the choice of K is not always a clear-cut decision. Different methods may suggest different values, and the final choice often depends on the specific context and objectives of the analysis. Domain knowledge and practical considerations, such as the interpretability and actionability of the resulting clusters, also play a crucial role in determining the appropriate number of clusters. As data scientists, it is our responsibility to approach the choice of K with a critical and analytical mindset. We must carefully consider the trade-offs between model complexity and interpretability, and be transparent about the assumption and limitation of our chosen approach. By leveraging a combination of direct and testing methods, and by incorporating domain expertise and practical considerations, we can make well-informed decisions about the optimal number of clusters in our k-means analysis. This allows us to uncover meaningful patterns and structures within our data, enabling us to extract valuable insights and drive data-driven decision-making. As we continue to push the boundaries of clustering techniques, the choice of K remains a crucial consideration. By approaching this challenge with rigor and creativity, we can unlock the full potential of k-means clustering and harness the power of unsupervised learning to solve complex problems and drive innovation across various domains. Once we have applied the k-means clustering algorithm to our data, it's crucial to assess the quality and validity of the resulting clusters. This evaluation process involves a combination of visual inspection, statistical analysis, and domain expertise. Let's explore some key considerations and techniques for evaluating the effectiveness of our k-means clusters. First and foremost, we can leverage pairwise plots to visually assess the separation between clusters. By selecting pairs of variables and plotting the data points colored by their assigned clusters, we can gain valuable insights into the distinctiveness of each cluster. If the clusters appear well separated in at least some of these plots, it indicates that the clustering algorithm has successfully captured meaningful patterns in the data. However, it's important to note that pairwise plots are most effective when dealing with a limited number of variables, as the number of possible pairwise combinations can quickly become overwhelming. Next, we should pay close attention to the size and composition of each cluster. If we observe clusters with very few data points, it may suggest that the chosen value of K is too high, leading to the creation of small, potentially spurious clusters. In such cases, it's worth considering decreasing the value of K to see if a more balanced and meaningful clustering structure emerges. On the flip side, if we have prior knowledge or expectations about certain splits or groupings in the data, but we don't observe them in the resulting clusters, it may indicate that the value of K is too low. In this scenario, increasing the value of K can potentially uncover more granular and relevant subgroups within the data. Another important aspect to consider is the proximity of cluster centroids to each other. If we find that some centroids are too close together, it suggests that the corresponding clusters may not be well separated and could potentially be merged. This situation often arises when the value of K is too high, leading to an oversegmentation of the data. By decreasing the value of k, we can potentially merge these close clusters and achieve a more parsimonious and interpretable clustering solution. It's worth noting that the evaluation of k-means clusters is an iterative process. We may need to experiment with different values of k and assess the resulting clusters using a combination of visual inspection, statistical measures, and domain knowledge. The goal is to strike a balance between capturing the underlying structure of the data and avoiding overfitting or underfitting. Moreover, it's crucial to consider the practical implications and actionability of the resulting clusters. Do the clusters align with our business objectives? Can we derive meaningful insights and make data-driven decisions based on the identified clusters? These questions highlight the importance of interpreting the clusters in the context of the specific domain and problem at hand. In summary, evaluating k-means clusters involves a multifaceted approach that combines visual inspection, statistical analysis, and domain expertise. By assessing cluster separation, size, composition, and central proximity, we can iteratively refine our clustering solution and ensure that it captures the underlying patterns and structure of the data. This evaluation process is critical for deriving meaningful insights, making informed decisions, and unlocking the full potential of k-means clustering in our data-driven endeavors. As we continue to leverage the power of unsupervised learning techniques like k-means, it's essential to approach cluster evaluation with rigor, curiosity, and a keen eye for detail. By doing so, we can uncover hidden gems within our data, drive innovation, and make a lasting impact in our respective fields. As we explore the realm of k-means clustering, it's crucial to understand the strengths and limitations of this powerful technique. Let's dive into the pros and cons of k-means and how they impact our ability to uncover meaningful patterns and insights within our data. On the positive side, one of the greatest advantages of k-means is its simplicity and ease of implementation. The algorithm is straightforward and can be readily applied to a wide range of datasets. This accessibility makes k-means a go-to choice for many data scientists and analysts, particularly when starting to explore the world of clustering. Another significant benefit of k-means is its ability to easily assign new data points to existing clusters. Once the clustering model is trained, we can efficiently determine the cluster membership of new observations based on their proximity to the cluster centroids. This feature is particularly valuable in real-time or streaming data scenarios, where we need to quickly categorize incoming data points. Moreover, k-means provides a concise and interpretable output in the form of cluster centroids. These centroids serve as representative points for each cluster, capturing the essence of the data points within them. This succinct representation allows us to summarize and understand the key characteristics of each cluster, facilitating data-driven decision-making and communication. However, it's important to acknowledge the limitation and challenges associated with k-means clustering. One notable drawback is its inability to handle categorical variables directly. K-means relies on numerical distance measures, which are not inherently defined for categorical data. To overcome this limitation, we often need to employ techniques like one-hot encoding or embedding to transform categorical variables into a numerical representation. Another potential pitfall of k-means is its sensitivity to initialization. The algorithm's performance can be influenced by the initial placement of the cluster centroids. Different initialization can lead to different clustering results, and in some cases, the algorithm may converge to suboptimal solutions. To mitigate this issue, it's common practice to run k-means multiple times with different initializations and select the best clustering based on a chosen criterion. K-means also assumes that all variables are measured on similar or compatible scales. If the variables have vastly different scales or units, the clustering results may be dominated by variables with larger magnitudes. To address this, It's crucial to preprocess the data by scaling or normalizing the variables before applying k-means. This ensures that each variable contributes equally to the clustering process. One of the most significant limitations of k-means is the requirement to specify the number of clusters, k, in advance. This can be challenging when we don't have prior knowledge about the inherent structure of the data. Determining the optimal value of k often involves a combination of domain expertise, trial and error, and evaluation techniques like the elbow method or silhouette analysis. Lastly, k-means has a tendency to produce clusters that are roughly spherical and of similar sizes. This property stems from the algorithm's objective of minimizing the within cluster sum of squares. While this may be desirable in some cases, it can also lead to suboptimal clustering if the true underlying structure of the data deviates significantly from this assumption. In conclusion, k-means clustering offers a powerful and accessible tool for uncovering patterns and structure within our data. Its simplicity, ease of implementation, and ability to assign new data points to existing clusters make it a valuable asset in our data science toolkit. However, it's crucial to be aware of its limitations, such as the inability to handle categorical variables directly, sensitivity to initialization, and the requirement to specify the number of clusters in advance. By understanding these pros and cons, we can make informed decisions about when and how to apply k-means, and how to interpret and leverage the resulting clusters for maximum impact. As we continue to navigate the exciting world of clustering and unsupervised learning, let us embrace the strengths of k-means while remaining mindful of its limitations. By doing so, we can unlock the full potential of this technique and drive meaningful insights and innovations across various domains. Hierarchical clustering, a powerful technique that unveils the intricate relationships and structures hidden within our data. Unlike traditional clustering methods, hierarchical clustering takes a unique approach by organizing clusters in a nested, tree-like structure known as a dendrogram. Picture a dendrogram as a visual representation of the clustering process, where each point along the bottom of the tree corresponds to an individual observation in our dataset. As we move up the tree, these individual points begin to merge, forming larger and larger groups or subclusters. The beauty of hierarchical clustering lies in its ability to capture the hierarchical relationships between these clusters, revealing the order in which they were combined. One of the key advantages of hierarchical clustering is that it doesn't require us to pre-specify the number of clusters, unlike methods such as k-means. Instead, the dendrogram provides a comprehensive overview of the clustering structure at various levels of granularity. This flexibility allows us to explore and interpret the data at different scales, from the most granular level of individual observations to the broadest level of the entire dataset. The dendrogram serves as a roadmap, guiding us through the clustering process and highlighting the relationship between clusters. By examining the dendrogram, we can gain valuable insights into the similarity and dissimilarity between observation and clusters. The height of each node in the dendrogram represents the distance or dissimilarity between the clusters being merged at that point. The higher the node, the more dissimilar the clusters are. One of the strengths of hierarchical clustering is its ability to uncover both compact and elongated clusters, as well as clusters with irregular shapes. This versatility makes it particularly useful when dealing with complex datasets where the underlying structure may not be immediately apparent. By capturing the hierarchical relationships, hierarchical clustering enables us to identify and interpret clusters at different levels of granularity, depending on our specific needs and goals. To determine the optimal number of clusters, we can examine the dendrogram and look for natural breaks or gaps in the tree structure. These breaks often indicate significant change in the similarity between clusters, and can serve as a guide for selecting an appropriate number of clusters. Additionally, domain knowledge and practical considerations can help inform our decision on where to cut the dendrogram to obtain the desired level of clustering. It's important to note that hierarchical clustering comes in two flavors: agglomerative and divisive. Agglomerative clustering starts with each observation as a separate cluster and progressively merges them based on their similarity. Divisive clustering, on the other hand, starts with all observations in a single cluster and recursively splits them into smaller clusters. The choice between these approaches depends on the specific characteristics of our data and the research question at hand. As we navigate the world of hierarchical clustering, it's crucial to consider the scalability and computational complexity of the algorithm. Hierarchical clustering can be computationally intensive, especially when dealing with large data sets. However, advancements in computational power and the development of efficient algorithms have made hierarchical clustering more accessible and practical in various domains. In conclusion, hierarchical clustering offers a powerful and intuitive approach to uncovering the intricate relationships and structures within our data. By organizing clusters in a nested, tree-like structure, hierarchical clustering provides a comprehensive view of the clustering process at different levels of granularity. The dendrogram serves as a visual guide, allowing us to explore and interpret the clustering results based on the specific needs and goals of our analysis. As we continue to harness the power of hierarchical clustering, let us embrace its flexibility, versatility, and ability to reveal hidden patterns and insights that can drive innovation and decision-making across diverse fields. Agglomerative clustering, a powerful bottom-up approach that reveals the intricate hierarchical structure within our data. This technique starts at the very foundation of the clustering process, gradually building up clusters from the individual observations themselves. At the heart of agglomerative clustering lies the concept of dissimilarity. To begin, we must define a measure that quantifies the dissimilarity or distance between observations. This could be based on metrics such as Euclidean distance, Manhattan distance, or even correlation, depending on the nature of our data and the research question at hand. By establishing this dissimilarity measure, we lay the groundwork for the clustering process. The agglomerative clustering algorithm embarks on its journey by initially assigning each observation to its own cluster. In other words, we start with a number of clusters equal to the number of observations in our dataset. This granular starting point allows us to capture the unique characteristics of each individual data point. From this initial state, the algorithm begins its iterative process of fusion. It identifies the two closest or most similar clusters based on the chosen dissimilarity measure and merges them into a single cluster. This fusion step forms the foundation of the hierarchical structure, as clusters are progressively combined based on their proximity or similarity. As the algorithm progresses, it continues to fuse the next closest clusters at each iteration. This process gives rise to a nested structure, where clusters at lower levels are subsumed into larger clusters at higher levels. The beauty of agglomerative clustering lies in its ability to capture the hierarchical relationship between clusters, revealing the natural groupings and subgroupings within our data. The fusion process continues until all observations belong to a single, all-encompassing cluster at the top of the hierarchy. This final cluster represents the entire dataset, with each subsequent level of the hierarchy providing a more granular view of the clustering structure. One of the key advantages of agglomerative clustering is its flexibility in terms of the number of clusters. Unlike some other clustering techniques, agglomerative clustering does not require us to pre-specify the number of clusters. Instead, we can examine the resulting dendrogram and make informed decisions based on the natural breaks or gaps in the hierarchy. This allows us to explore and interpret the clustering results at different levels of granularity, depending on our specific goals and domain knowledge. It's important to note that the choice of the similarity measure and the specific algorithm used for cluster fusion can impact the resulting clustering structure. Common algorithms include single linkage, complete linkage, and average linkage, each with its own characteristics and strengths. The choice of algorithm depends on the nature of our data and the desired properties of the resulting clusters. As we navigate the landscape of agglomerative clustering, it's crucial to consider the computational complexity of the algorithm. Agglomerative clustering can be computationally intensive, especially for large datasets, as it requires calculating pairwise dissimilarities between all observations. However, advancements in computational power and the development of efficient data structures have made agglomerative clustering more feasible and practical in various domains. In conclusion, agglomerative clustering offers a powerful bottom-up approach to uncovering the hierarchical structure within our data. By starting with individual observations and iteratively fusing the closest clusters, agglomerative clustering reveals the natural groupings and subgroupings in a nested fashion. The resulting dendrogram provides a comprehensive view of the clustering structure, allowing us to explore and interpret the results at different levels of granularity. As we harness the power of agglomerative clustering, let us embrace its flexibility, adaptability, and ability to uncover meaningful patterns and insights that can drive decision-making and innovation across diverse fields. When it comes to agglomerative clustering, one of the crucial components is the dissimilarity measure. This measure serves as the backbone of the clustering process, guiding the algorithm in determining the proximity or similarity between observations and clusters. Let's explore the common approaches to defining dissimilarity and their implication for the resulting clustering structure. In the realm of agglomerative clustering, distance-based dissimilarity measures are widely used and well established. These measures quantify the dissimilarity between observations based on the concept of distance in a multi-dimensional feature space. The choice of distance metric depends on the nature of our data and the specific characteristics we wish to capture. Among the popular distance metrics, Euclidean distance stands out as a versatile and intuitive choice. It measures the straight-line distance between 2 points in the feature space, taking into account the differences across all dimensions. Euclidean distance is particularly suitable when the features are continuous and the differences in each dimension are equally important. Another notable distance metric is the Manhattan distance, also known as the city block distance, or L1 norm. This metric calculates the sum of the absolute differences between the coordinates of 2 points. Manhattan distance is especially useful when the features represent variables that are not necessarily continuous, or when the differences in each dimension have different scales or units. For binary or categorical features, the Hamming distance comes into play. It measures the dissimilarity between two observations by counting the number of positions at which the corresponding features differ. Hamming distance is commonly used in scenarios where the presence or absence of certain attributes is more relevant than their actual values. In text mining or natural language processing, the cosine distance is often employed. It measures the cosine of the angle between two vectors representing the observations. Cosine distance is particularly effective when dealing with high-dimensional sparse data, such as text documents, where the magnitude of the feature values is less important than their relative orientations. While distance-based dissimilarity measures are prevalent, it's important to note that correlation-based similarity measures can also be used in agglomerative clustering, although they are less common. Correlation-based measures focus on the patterns and relationships between features rather than their actual values. They assess the similarity between observations based on the correlations of their feature profiles. This approach can be beneficial when the actual values of the observation may be far apart, but the relative patterns or trends are of interest. Once we have defined the dissimilarity measure, The next step is to determine how the distance between clusters is calculated. This is where the concept of linkage comes into play. Linkage refers to the method used to compute the dissimilarity between two clusters based on the pairwise dissimilarities of their constituent observations. The most common types of linkage include single linkage, complete linkage, average linkage, and centered linkage. Single linkage considers the minimum distance between any two observations from different clusters, while complete linkage takes the maximum distance. Average linkage calculates the average distance between all pairs of observations from different clusters, providing a balanced approach. Centered linkage, on the other hand, computes the distance between the centroids of the clusters. The choice of linkage method can significantly impact the resulting clustering structure. Single linkage tends to produce elongated or chained clusters, while complete linkage favors compact and spherical clusters. Average linkage strikes a balance between the two extremes, often yielding more balanced and interpretable clusters. The selection of linkage depends on the desired properties of the clusters and the specific characteristics of the data. When it comes to agglomerative clustering and distance-based similarities, there are four prominent approaches that deserve our attention: single linkage, complete linkage, average linkage, and centered linkage. Each of these methods offers a unique perspective on how to measure the proximity between clusters and ultimately shape the resulting hierarchical structure. Let's dive into the intricacies of these approaches and explore their implications. First, let's consider single linkage, also known as the nearest neighbor approach. In single linkage, the distance between two clusters is determined by the minimum distance between any 2 points belonging to those clusters. This method focuses on the closest pair of observations, regardless of which cluster they belong to. Single linkage has a tendency to produce elongated or chained clusters, as it can bridge gaps between clusters based on the proximity of individual observations. This approach is particularly sensitive to noise and outliers, as a single close pair can lead to the merging of clusters that may be otherwise distinct. On the other end of the spectrum, we have complete linkage, also referred to as the furthest neighbor approach. In contrast to single linkage, complete linkage considers the maximum distance between any 2 points from different clusters. This method ensures that all observations within a cluster are within a certain maximum distance from each other. Complete linkage tends to produce compact and spherical clusters, as it requires all observations in a cluster to be similar to each other. This approach is less susceptible to noise and outliers compared to single linkage, as it takes into account the worst-case scenario when merging clusters. Moving on, we have average linkage, which offers a balanced approach between the extremes of single and complete linkage. In average linkage, the distance between two clusters is calculated as the average distance between all pairwise proximities of observations from different clusters. This method considers the overall similarity between clusters, taking into account the contributions of all observations. Average linkage tends to produce clusters that are more balanced and interpretable, as it strikes a compromise between the chaining effect of single linkage and the compactness of complete linkage. It is less sensitive to noise and outliers compared to single linkage, while allowing for more flexibility in cluster shapes compared to complete linkage. Finally, let's discuss centered linkage, which introduces a different perspective on measuring cluster proximity. In centered linkage, the distance between two clusters is determined by the distance between their centroids. The centroid of a cluster is the average position of all observations within that cluster. Centroid linkage focuses on the central tendency of clusters and merges them based on the proximity of their centroids. This approach can be computationally efficient, as it only requires calculating the distances between cluster centroids rather than all pairwise distances. However, It is important to note that the centroid of a merged cluster may not necessarily represent an actual observation, which can lead to some loss of information. The choice of linkage method in agglomerative clustering has a significant impact on the resulting hierarchical structure. Each approach has its own strengths and weaknesses, and the selection depends on the specific characteristic of the data and the desired properties of the clusters. Single linkage is suitable when we expect clusters with irregular shapes and want to capture the connectivity between observations. Complete linkage is preferred when we prioritize compact and well-separated clusters. Average linkage provides a balanced approach that considers the overall similarity between clusters. Centered linkage offers computational efficiency, but may sacrifice some granularity in the clustering process. In conclusion, the distance-based similarities used in agglomerative clustering, namely single linkage, complete linkage, average linkage, and centered linkage, offer diverse perspectives on measuring the proximity between clusters. Each approach has its own merits and limitations, influencing the shape, compactness, and interpretability of the resulting clusters. By understanding the characteristics and implication of these linkage methods, we can make informed decisions when applying agglomerative clustering to our data. As we continue to explore the vast landscape of clustering techniques, let us harness the power of these approaches to uncover meaningful patterns, gain valuable insights, and drive innovation across various domains. While agglomerative clustering is the most common approach in hierarchical clustering, today we will explore an alternative perspective known as divisive hierarchical clustering. This top-down approach offers a unique way to uncover the hierarchical structure within our data, starting from a single, all-encompassing cluster and recursively dividing it into smaller, more refined clusters. Let's embark on this fascinating journey and discover the intricacies of divisive clustering. In contrast to agglomerative clustering, which starts with individual observations and gradually merges them into larger clusters, divisive hierarchical clustering takes the opposite route. It begins with a single, large cluster that encompasses all the observation in our dataset. This initial cluster represents the entire population, capturing the overall characteristics and variability of the data. From this starting point, the divisive clustering algorithm embarks on a recursive process of division. At each stage, the algorithm selects the cluster with the largest dissimilarity between any two of its observations. This cluster is deemed the most heterogeneous and is chosen to be divided into smaller, more homogeneous subclusters. The criterion for selecting the cluster to divide is based on the notion of maximizing the dissimilarity or distance between observations within the cluster. The division process continues iteratively, with each selected cluster being split into smaller clusters based on the dissimilarity criterion. This recursive partitioning of clusters allows us to capture the hierarchical structure of the data, revealing the natural groupings and subgroupings at different levels of granularity. As the algorithm progresses, the number of clusters increases, and each cluster becomes more specialized and focused on specific characteristics of the observation it contains. One of the key aspects of divisive hierarchical clustering is that it continues the division process until each cluster contains only a single observation. This means that at the lowest level of the hierarchy, each individual observation forms its own cluster. This granular representation allows us to examine the data at the finest level of detail, capturing the unique characteristics of each observation. The divisive clustering approach offers several advantages. Firstly, it provides a top-down perspective on the hierarchical structure of the data. By starting with a single cluster and recursively dividing it, we can explore the data at different levels of granularity, gaining insights into the broad patterns and progressively zooming in on the finer details. This hierarchical representation enables us to understand the relationships and similarities between clusters at various scales. Secondly, divisive clustering can be computationally efficient, especially when dealing with large datasets. By focusing on dividing clusters rather than merging them, the algorithm can potentially reduce the number of pairwise comparisons required. This can lead to faster execution times and more scalable solutions, particularly when the number of observations is substantial. However, it's important to note that divisive hierarchical clustering also has its challenges. The selection of the dissimilarity measure and the criterion for dividing clusters can have a significant impact on the resulting hierarchy. Different choices may lead to different cluster assignments and interpretations. Additionally, the recursive nature of the algorithm means that any errors or suboptimal divisions made in the early stages can propagate down the hierarchy, affecting the subsequent divisions. In conclusion, divisive hierarchical clustering offers a unique perspective on uncovering the hierarchical structure within our data. By starting with a single, all-encompassing cluster and recursively dividing it based on dissimilarity, divisive clustering provides a top-down approach to exploring the data at different levels of granularity. It allows us to understand the broad patterns and progressively focus on the finer details, revealing the natural groupings and subgroupings within the data. While divisive clustering has its advantages, such as computational efficiency and a top-down perspective, it also presents challenges in terms of selecting appropriate dissimilarity measures and handling potential errors in the division process. As we navigate the landscape of hierarchical clustering, let us consider the strengths and limitations of divisive clustering and harness its power to gain valuable insights and make informed decisions across various domains. Fuzzy clustering, a powerful technique that embraces the inherent uncertainty and ambiguity present in many real-world datasets. Unlike traditional clustering approaches that assign observation to definite or crisp clusters, fuzzy clustering allows for a more nuanced and flexible representation of cluster membership. Let's explore the concepts and implications of fuzzy clustering and how it can revolutionize our understanding of data structures. At the core of fuzzy clustering lies the application of fuzzy set theory, a mathematical framework that extends the notion of binary membership to a continuous spectrum of possibilities. In fuzzy set theory, an observation can belong to multiple sets simultaneously with varying degrees of membership. This concept is particularly relevant in clustering, where the boundaries between clusters may not always be clear-cut, and observations may exhibit characteristics of multiple clusters. In fuzzy clustering, each observation is assigned a set of membership probabilities, denoted as U, which indicate the degree to which the observation belongs to each cluster. These membership probabilities range from 0 to 1, with 0 indicating no membership and 1 indicating full membership. The sum of an observation's membership probabilities across all clusters typically equals 1, ensuring a comprehensive representation of its cluster associations. The membership probabilities provide a rich and informative characterization of the data structure. They allow us to capture the uncertainty and ambiguity inherent in real-world datasets, where observations may not fit neatly into a single cluster. By assigning membership probabilities, fuzzy clustering acknowledges that an observation can exhibit characteristics of multiple clusters simultaneously, reflecting the complex and overlapping nature of real-world phenomena. One of the key advantages of fuzzy clustering is its ability to handle datasets with overlapping or ill-defined cluster boundaries. In traditional clustering approaches, an observation is forced to belong to a single cluster, even if it exhibits strong similarities to multiple clusters. Fuzzy clustering, on the other hand, allows for a more realistic representation of the data, capturing the gradual transition and overlaps between clusters. This flexibility is particularly valuable in domains such as pattern recognition, image segmentation, and customer segmentation, where the boundaries between categories may be blurred. Moreover, Fuzzy clustering provides a rich set of tools for analyzing and interpreting the results. By examining the membership probabilities, we can gain insights into the strength and certainty of an observation's association with each cluster. We can identify observations that strongly belong to a single cluster, as well as those that exhibit significant membership in multiple clusters. This information can be utilized for various purposes, such as anomaly detection, data visualization, and decision making. The application of fuzzy clustering extends beyond the realm of data analysis and has profound implications across various domains. In marketing, fuzzy clustering can be employed to segment customers based on their purchasing behaviors, preferences, and demographics, allowing for more targeted and personalized marketing strategies. In medical research, fuzzy clustering can aid in the identification of disease subtypes or the stratification of patients based on their clinical characteristics, enabling more precise and individualized treatment approaches. However, it is important to note that fuzzy clustering also presents its own set of challenges. The selection of an appropriate fuzzy clustering algorithm and the determination of the optimal number of clusters require careful consideration. The interpretation of membership probabilities and the validation of fuzzy clustering results may also require domain expertise and statistical rigor. In conclusion, fuzzy clustering represents a paradigm shift in our understanding of data structures, embracing the uncertainty and ambiguity present in real-world data sets. By assigning membership probabilities to observations, fuzzy clustering allows for a more nuanced and flexible representation of cluster associations. It provides a powerful framework for handling datasets with overlapping or ill-defined cluster boundaries, enabling more realistic and informative analyses. As we continue to navigate the vast landscape of data science and machine learning, let us harness the potential of fuzzy clustering to uncover hidden patterns, gain deeper insights, and make more informed decisions across various domains. While we have been exploring the fascinating world of clustering observations, we will shift our focus to another crucial aspect of data analysis, the clustering of variables. This approach takes a different perspective, aiming to identify variables that exhibit strong relationships and similarities in their values. Let's delve into the concepts and implications of variable clustering and how it can provide valuable insights into the underlying structure of our data. In contrast to the clustering of observations, which primarily relies on measures of distance to group similar data points together, variable clustering focuses on the relationships and dependencies among the variables themselves. It seeks to uncover the hidden patterns and associations that exist within the multidimensional space of our dataset. At the heart of variable clustering lies the notion that the relative values of variables contain valuable information about the similarity or dissimilarity of observations. When variables exhibit similar patterns or trends across observations, it suggests a strong relationship between those variables. By identifying these relationships, we can gain a deeper understanding of the underlying mechanism and dependencies within our data. Conversely, the relative values of multivariate observations also provide insights into the similarity of variables. When observations possess similar values across a set of variables, it indicates that those variables are closely related and may be measuring similar aspects or characteristics of the data. This information is crucial for feature selection, dimensionality reduction, and data interpretation. One of the primary techniques employed in variable clustering is correlation analysis. By calculating the pairwise correlation between variables, we can quantify the strength and direction of their linear relationships. Variables with high positive correlations tend to move in the same direction, while variables with high negative correlation exhibit an inverse relationship. Correlation-based clustering algorithms, such as hierarchical clustering or key-on-means clustering, can be applied to group variables based on their correlation patterns. Another approach to variable clustering is through the use of dimensionality reduction techniques, such as principal component analysis, PCA, or factor analysis. These methods aim to identify the underlying latent factors or components that explain the variability and relationships among the variables. By projecting the data onto a lower dimensional space defined by these latent factors, we can uncover the hidden structure and groupings of variables. The benefits of variable clustering are manifold. Firstly, it enables us to identify redundant or highly correlated variables, which can be helpful in feature selection and data preprocessing. By eliminating redundant variables, we can simplify our models, reduce computational complexity, and mitigate the curse of dimensionality. This is particularly important in high-dimensional datasets, where the number of variables far exceeds the number of observations. Secondly, variable clustering provides valuable insights into the underlying relationships and dependencies within our data. By identifying groups of variables that exhibit strong associations, we can gain a deeper understanding of the complex interactions and mechanisms at play. This knowledge can inform hypothesis generation, guide further analysis, and support decision-making processes. Moreover, variable clustering can aid in data visualization and interpretation. By grouping related variables together, we can create more meaningful and interpretable visualizations, such as heat maps or network graphs. These visualizations can highlight the patterns and relationships among variables, facilitating the communication of insights to stakeholders and domain experts. However, it is important to note that variable clustering also presents its own set of challenges. The choice of similarity measure, such as correlation or distance, can have a significant impact on the resulting clusters. Additionally, the interpretation of variable clusters requires domain knowledge and careful consideration of the underlying relationships and mechanisms. As we continue to delve into the world of clustering, one of the most critical and challenging aspects is the validation and evaluation of the resulting clusters. Unlike supervised learning methods, where we have the luxury of ground truth labels to guide our assessment, clustering lacks a universally accepted gold standard for determining the quality and validity of the obtained clusters. Today, we will explore the various approaches and techniques used to tackle this complex task and ensure the reliability and usefulness of our clustering results. Validation is a crucial step in the clustering process, as it allows us to assess the meaningfulness and robustness of the identified clusters. It helps us determine whether the discovered patterns and groupings truly reflect the underlying structure of the data, or if they are merely a result of chance or noise. Without proper validation, we risk making decisions based on spurious or unreliable clusters, leading to suboptimal outcomes and misguided insights. One of the primary goals of cluster validation is to identify non-random structure within the data. We want to ensure that the clusters we obtain are not a mere artifact of the clustering algorithm, but rather a genuine reflection of the inherent patterns and relationships present in the data. Various statistical tests and measures, such as the silhouette coefficient or the gap statistic, can be employed to assess the presence of non-random structure and quantify the strength and distinctiveness of the clusters. Another crucial aspect of cluster validation is determining the correct number of clusters. Many clustering algorithms, such as k-means or hierarchical clustering, require the specification of the desired number of clusters as an input parameter. However, in real-world scenarios, the optimal number of clusters is often unknown a priori. To address this challenge, various techniques have been developed, such as the elbow method, the silhouette method, or the Bayesian information criterion, BIC. These methods aim to identify the point of diminishing returns, where increasing the number of clusters no longer provides substantial improvements in terms of cluster compactness or separation. Moreover, cluster validation involves assessing the extent to which the obtained clusters match the underlying structure of the data. We want to ensure that the clusters capture meaningful and interpretable patterns that align with our domain knowledge and expectations. Measures such as the adjusted RAND index or the normalized mutual information can be used to quantify the agreement between the obtained clusters and external validation criteria, such as expert annotations or known class labels. In addition to evaluating individual clustering solutions, cluster validation also plays a crucial role in comparing and selecting the better sets of clusters among multiple candidates. Different clustering algorithms or parameter settings may yield different partitions of the data, and we need a systematic way to determine which clustering result is most suitable for our purposes. Techniques such as cross-validation, stability analysis, or consensus clustering can be employed to assess the robustness and reproducibility of the clusters across different subsets of the data or under perturbations. It is important to note that cluster validation is an iterative and exploratory process. It often involves a combination of quantitative measures, visual inspection, and domain expertise. The choice of validation metrics and approaches depends on the specific characteristics of the data, the goals of the analysis, and the assumption underlying the clustering algorithm. It is crucial to interpret the validation results in the context of the problem at hand and to consider multiple perspectives and criteria when making decisions based on the clustering results. In conclusion, cluster validation and evaluation are essential components of the clustering process, ensuring the reliability, meaningfulness, and usefulness of the obtained clusters. Despite the lack of a universal consensus on the best validation method, various approaches have been developed to identify non-random structure, determine the correct number of clusters, assess the match with the underlying data, and compare different clustering solutions. By employing a combination of quantitative measures, visual inspection, and domain expertise, we can navigate the complexities of cluster validation and make well-informed decisions based on the clustering results. As we continue to harness the power of clustering in various domains, let us prioritize the importance of validation and strive for robust, interpretable, and actionable insights that drive innovation and solve real-world challenges. As we conclude this lesson, I want to express my genuine hope that you found the material both informative and engaging. It has been a pleasure presenting this content to you, and I sincerely wish you all the best in your future endeavors. Thank you for your attention and participation.